Keeping in mind that pointers are simply variables, it makes sense that we can perform mathematical operations on them. Due to their nature, though, the operations that are allowed on pointers are limited to addition and subtraction. It does not make sense to multiply addresses together, nor does it make sense to divide one address into another address. So we are limited to either adding, subtracting, incrementing, or decrementing an address. In review, we can calculate the address of an element of an array. In this case, what is the address of element 0? We can take that address and then assign it into a variable that is designed to store an address. And if we go to that address, in this case, is designed to point to a car. That means that if I am pointing to an array, and it's designed to store letters, ASCII letters like B, R, A, D, for example. And if it's a string, it would be terminated by the special null character. And if we were to pretend that this was stored in memory at address 1000, the next one would be at address 1001. The A would be at address 1002. The D would be at address 1003. And the null would be located at address 1004. Element 0, element 1, element 2, element 3, element labeled 4. In this case, the address 1000 would be placed into the variable called PTR name. It makes sense if I want to point to the next car that this address needs to be incremented by 1. PTR name would then point to the next character. The address of the pointer has been incremented by the size of the variable it's been designed to point to. In this case, PTR name has been designed to point to a car, so incrementing that variable increments it enough to point to the next car. Looking at this diagram shows that this variable, if it has been declared to hold an address, and if we go to that address is designed to store a car, if it's being assigned the value 1000 to point to B, incrementing that pointer will go to that address of the, go to this variable, take its contents and increase it by 1. Notice that PTRZ name is a variable and as such has an address. It lives someplace in RAM. In this case, we've said that it lives starting at address 2005. Notice that we're incrementing its contents. We're incrementing the address stored within the array. We're not incrementing its own address. We're incrementing the contents in order to point to the next character in the array. Looking at another example, here we have an array called temperatures that contains 7 values. It's been designed to store integers as 2-byte values, and we're mimicking that. 1000, 1002, 1004, 1006, 1008, and these are represented as decimal numbers to ease our calculations here. Normally addresses would be shown as hexadecimal, but for this presentation we'll assume that all these numbers are in decimal. We have some values stored within this integer array or array of integers. This would be element labeled 0, element labeled 1, element labeled 2, element labeled 3, element labeled 4, element labeled 5, and element labeled 6. Again, showing a variable of type pointer designed to store an address We're assuming that it's been assigned a value of 1006 in order to point to this element of the array, which happens to be element labeled 3. You'll notice in similar code where we're incrementing the variable of type pointer, notice that instead of incrementing by 1, is incrementing by the size of an integer. In order to point from 1 to the next integer, the compiler has incremented this by 2. So this piece of information is used by the compiler when it's adjusting addresses. It adjusts by the size specified to the left of the asterisk. We can also compare addresses. So in this case, if P1 has been designed to store an address, and if we go there, we're going to find a car, and P2 has been designed to store an address, and if we go there, it's designed to hold a car. Then we can take the address of a variable, put it in P1. We can then assign P1, the contents of P1, to be assigned to the variable P2. And here we can actually check to see whether those addresses are the same. P1 is designed to store an address. P2 is designed to store an address. We have an address on the left. We have an address on the right of the equivalency check. In this case, P1, the contents of P1 should be equivalent to the contents of P2. They should hold the same address, so therefore we should say that P1 points to the same variable as P2.